the theory of general relativity predicts its own downfall inside black holes and at the Big Bang. And now you can say two things, right? So now what now? And of course, the general law, the general interpretation of these singularities is not that they're really there, that nature is somehow singular. No, the general interpretation is that the classical theory of relativity is inadequate to describe those most extreme phenomena. And so that quantum gravitational physics becomes important in those two really extreme corners of the universe, inside black holes and at the Big Bang.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 135. And this episode is with Thomas Hertog, the first Belgian ambassador to the Robinson's podcast Multiverse, who is professor and head of theoretical physics in the Department of Physics and Astronomy at KU, let's see if it's Leuven or Leuven. Leuven sounds more Belgian to me, so I'm going to go with Leuven in Belgium. And among Thomas's many other career accolades, he was a hand-picked doctoral student and then close collaborator of Stephen Hawking, who I imagine is, along with Einstein, probably among the most recognized physicists of all time. And in this episode, Thomas and I discuss his book that came out earlier this year on the origin of time, Stephen Hawking's final theory. We start off by talking about their collaboration, which you can imagine would have been unique given Hawking's physical limitations, his fame, his character, all of these constraints. And then we get into his philosophical views, which were rather pessimistic. He's well known for saying philosophy is dead. Then post-philosophy, since it is dead, physics comes in. We begin with the basics of cosmological inflation, the expansion of space, and how this leads back to the Big Bang, because Thomas and Stephen worked a great deal together on cosmology, which is the field of astronomy or subfield concerned with the birth and subsequent development of the universe. And we get into the three stages of Stephen's work, or at least that's how I thought of it, and Thomas said I was at least on the right track. The last of which, though, which was the final theory referenced in the title of Thomas's book, and it was this theory that he and Thomas put forth called Top-Down Cosmology, and this theory we arrive at toward the end of our conversation as we get to the origin of time. So one caveat here worth mentioning is that almost immediately after Thomas and I began recording, there were some connection issues that resulted in our not being able to see one another while we were talking. So while our videos are still there, they were recorded. If you're watching on YouTube, we couldn't see each other. So there were a few moments where one of us couldn't tell whether or not the other was about to speak or was done speaking or was thinking. So maybe we cut each other off or pause a little bit more than usual, but I don't think it causes any problems. So please review, like, comment, subscribe. All these things are endlessly appreciated. And without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Thomas. From reading on the origin of time, which for our listeners, though I will have said this in the introduction, it recounts the development of Stephen Hawking's cosmology and then your own collaboration with him. I got the distinct sense that you didn't get into physics because he was a particular hero of yours, but that rather the collaboration came about by chance or because of your really good test scores. But prior to Hawking, were you always fascinated by cosmology? Was that the area of physics that sparked your interest in the field? or your entry into the field?
Not really, although gradually during bachelor and master education in physics, I sort of discovered first Einstein's theory of relativity and then cosmology. And then by the time I met Stephen, yes, I had made up my mind. But it wasn't a childhood thing for me. No, I came to physics because I liked playing with math. And I thought theoretical physics is just a really cool arena to play with maths.
Well, I'd like to start before we get into the physics and the playing with math with what it was like to work with Stephen as a person, since, I mean, he's not only like a mythical figure in the zeitgeist, but he's somebody who, I mean, I could tell from reading that he was incredibly important to you as a mentor and a collaborator. And the main thing that I'm curious about, just from my own work with professors, is whether he was the sort of advisor who would give you a problem and send you off on your own to work on it, or whether it was really very collaborative. And I think this must be all the more complex because of his physical limitations and then the obligations that came from whisking around on jets all the time from his fame.
Right. All right, that's a good question. He was neither type of mentor that you describe. He was not the kind of mentor that would just send you off. That's certainly not how I've known him, certainly not in that stage of his career, in which he worked, in fact, quite closely with his students. He gave us problems, or he put us in certain directions which were close to his heart. Then, on the other hand, of course, he was also not the kind of mentor that would participate in the calculations and follow up closely. So, because of course he was, as you say, too busy, it was difficult anyway to write down an equation for him. So that was also not the way it was working. So somehow I think he had a sort of a unique blend. His mentorship was close in certain ways, close, for instance, in the conceptual sides of problems, and hands-off when it came to actual calculations. So I think it was sort of a mix, at least in that time, in that sort of span of his career that I've known him as a mentor in the late 90s. Of course, by then, it may have been different in the 80s. And it was certainly impossible later in the early 2000s when communication with Stephen became much more difficult. But in the 90s, it was an exciting time in cosmology. There were lots of new observations. It was an exciting time in theoretical physics because ADS-CFT and holography was being discovered. Inflation was being tested. So, and Stephen's book, A Brief History of Time, was out. So he was back into research, and he was back into research in a way which involved very much his students. That's at least how I have experienced it. Of course, this whole collaboration that I describe in my book, it spans a period of more than 20 years. So our relation very much evolved during those years. That's obvious, right? I'm not sure that answers your question, but at least
No, it definitely does. You take a lot of care in your writing to discuss the philosophy of science, and I really appreciated that and how it's changed over time, but at the same time, quite early in the book, you recount a conversation with Stephen in which he told you point blank that philosophy is dead. And this is something that I've heard a lot of people quote him on, but very few people have the sort of insight that you do into what he was thinking at the time. So I'm wondering what you think he had in mind when he said philosophy is dead.
Right, because of course Stephen's physics and certainly his cosmology is perceived as philosophically rather productive in certain ways. I think what he meant, at least that's how I understood it, is that philosophy without consideration of new scientific developments, new developments in his case in fundamental physics and cosmology, is sort of, walking blindly. He held this conviction that by delving deeper and deeper in the questions of science would ultimately prove more productive. In a sense, I think he felt that someone like Einstein, who failed to predict the expansion of the universe based on his philosophical prejudices, so that someone like Einstein had been guided too much by some sort of philosophical position. And I've always felt that he tried to sort of not take too much of a position and rather attempt to read what his physical theories were trying to tell him. On the other hand, I think it's also that statement, the statement that you're referring to, philosophy is dead. It's also, of course, a typical Hawkingian kind of exaggeration or controversial kind of statement, in which reflects, I think, to some extent, the discussions he had with philosophers, which hadn't always been particularly fruitful, in his opinion. So, as with many Hawkingian statements, this had a sort of a controversial, almost joking, poking side to it, and a serious side to it. Of course, and also, a final point perhaps is, I believe he made that statement long ago. The kind of how, in the 80s, I believe. I think that throughout my collaboration with Stephen, in which we stumbled upon this discovery that quantum theory allows for a whole new view of the cosmos, which we call, as you mentioned, which we call a top-down view, which we called a view from the inside. The whole new cosmology that we developed has philosophical implications. And I think Stephen himself has been quite surprised by these. So you see, it's a very complex statement, which I can't really summarize in sort of one or two lines. There are different sides to it.
No, but I think you hit all of the main points, and it was exactly the sort of answer that I was hoping for. So I'll respond in a few different ways. But one, by the end of the book, I totally understood, I think, the typical Hawking sense of humor. And I liked how you mentioned, because he communicated largely, by typing in his own fashion and very slowly, that he developed this technique of making jokes that only strike at the very last word. But he was a very witty and funny and dramatic person in this sense. And then the second thing I wanted to say is you you said, I think, that philosophy that doesn't take into account the new developments in physics is walking blindly. And I recently spoke with the chair of the philosophy department at NYU, Paul Bogassian, about this, and Stephen's quote came up. And Paul pointed out, I think rightly, that people who aren't philosophers and have this outside view, they can't really distinguish between the good philosophy and the bad philosophy, of which there's a lot more bad philosophy than good philosophy. And he might have conflated philosophy at large with maybe the postmodernism at the time. And if Hawking were speaking with very well-informed philosophers of physics like Sean Carroll or Tim Maudlin or David Albert, he might not have had this sense that philosophy is dead. It's very much alive if you look in the right places. And then the last thing I wanted to say was, it is quite interesting that Einstein was quite philosophically informed, and my understanding is that in many ways this did aid his thinking in some dimensions. But you said that he sort of failed to perceive or predict the expansion of the universe because of his philosophical prejudices that the universe should be a sort of static thing. And that's exactly where I wanted to get to as we move to the physics. So I wanted to start by talking about a conception broadly of laws and cosmology. And I think the right place to start is with the basics of cosmological inflation as discovered and then developed by Hubble and Lemaitre, among others. And parenthetically, before you can help out with that, is we're so familiar with the idea of the Big Bang today that it's pretty much unfathomable to wrap one's head around how heavily it was ridiculed and protested in the 20th century, which your writing made very clear.
Oh, yeah. So that's the story of the late 20s and the early 30s. Well, I think the way it went was as follows. To credit Einstein, it seems clear to me that he realized all too well, pretty much immediately when he discovered general relativity, that this could have major implications for cosmology, for our understanding of the universe as a whole. Then at that point, somehow he explored those implications, but somehow at that point, his prejudices kicked in, and he began to search for basically an old Newtonian-like static eternal universe in his theory. And he found one by, in fact, slightly modifying his theory and including the famous dark energy component, the famous dark cosmological constant. Around that same time, the very first observations were rolling in, indicating that other galaxies other than the Milky Way, are moving away from us. Notably, Vesto-Slipher in Flagstaff, so near the Grand Canyon, was making those observations. I believe Einstein was probably not aware of those observations. So this is the late 1910s, 1917, 18, and so forth. So what then happened, independently, in fact, in Russia by Friedman and as you say by Lemaitre in Belgium and in the States, is that a new generation like Friedman and Lemaitre looked at Einstein's theory of relativity and its cosmological implications with sort of, perhaps more of an open mind, and found that this static universe of Einstein was unstable, was just nonsense, essentially. And they found that the theory essentially predicted that the universe should either expand or contract. What is interesting about the figure of Lemaitre, who was a priest and an astronomer, is that he was very well aware not only of Einstein's theory, but also of these early observations of Slipher indicating that galaxies were moving away from us. So Lemaitre was pursuing the cosmological implications not on a purely idealistic theoretical basis, but having in mind these observations, and of course in his first paper, in which he posited the expansion of the universe, he immediately derives the consequence that we should then see, if the universe expands, we should see the other galaxies moving away from us. So he was much more in tune with the astronomical observations. And I think that's really the key difference. And then, of course, as we all know, very shortly afterwards, Hubble, with a much more powerful telescope on Mount Wilson in Pasadena, right, was able to confirm that the further away the galaxies are, the faster they seem to be moving away from us. And Lemaitre had already given the explanation, right? Because space is expanding. So, yeah, what is the lesson there? The lesson is perhaps, that in the complete absence of observations or experiments, it's just very difficult, right? Physics is all about this interaction, this interplay, this dialogue between fundamental theory and experiments and observations. The same was playing out in my view in the 1990s, so the last decade of the 20th century, when with the observations of the acceleration of the expansion, with the observations of the fluctuations in the microwave background sky, you have these decades, you have these eras, these periods in which our field is really fundamentally transforming. And often this is happening because in a close interaction between theoretical insights and new cosmological observations. We can only hope that we are gearing up for the next such phase.
And this expansion that you just described, it led theoretically through twists and turns to the hypothesis of the Big Bang. And I think it was Lemaitre who coined this phrase, the primeval atom, but from which everything came out. But what did George Gamow retrodict? And I'm glad for the opportunity to use this word. It was a new one for me. And that future observations have supported happened in the first few minutes after the Big Bang. And the just to give you some idea of where I'm heading, I think that your answer to this question should lead us toward the anthropic principle, which will then bring us back, of course, to your and Stephen's collaboration.
Right. So you're right that when Lemaitre discovered the expansion of the universe in 1927, when working with Einstein's theory of relativity, interestingly, in 1927, the very first of his papers on the expansion, there was no Big Bang. In fact, Lemaitre had started from Einstein's static universe and had realized that the slightest perturbation would turn this into an expanding universe. But then, interestingly, a few years later, he realizes, well, okay, this static universe, who put it there? It's an unstable thing. It doesn't make any sense. And so he realizes that a much more natural beginning is one in which there's a genuine origin, a genuine Big Bang, an origin of time. And so he goes on to construct all sorts of expanding universes. As you say, he sort of evokes the idea that the origin of time, what we call today the Big Bang, is some sort of primeval atom, which he doesn't quite specify. I think he coins that term to indicate that somehow quantum theory should become important at these very earliest stages of the universe. Gamow, as you say, developed that theory into a hot Big Bang. So Gamow essentially applied the new nuclear physics to that problem and famously discovered that if there was a Big Bang, if there was a hot Big Bang, if the universe was once very small and hot, there should be an afterglow, there should be a remnant radiation of that era, which we now know as the cosmic microwave background radiation. But be it Gamow's model or the current, the present day model or current refined theory of Big Bang cosmology with inflation and everything, or even Lemaitre's original theory, there's something profoundly strange about this whole conception. In order to get a universe out of a Big Bang, in which complex structures can develop, in which galaxies can grow, in which eventually life can form, that doesn't come out just out of any Big Bang. It requires very special conditions in the beginning. Even just to have an arrow of time, you need to have a very low entropy in the beginning. You can't have a universe that expands too fast with too much dark energy, or because it will end up empty. You can't have a universe that expands too slowly because that will recollapse, and so forth and so forth. So there's a long list of properties that the universe must have in order for it to be a habitable place. And so the Big Bang, in some sense, is in some sense both the cornerstone and the Achilles heel of modern cosmology. It's the cornerstone because clearly it works very well. It's a model of an expanding universe that fits many, many observations. It's the Achilles heel because it requires supremely fine-tuned initial conditions in order to produce the universe like we observe it. And some people have evoked the anthropic principle as an explanation. Stephen too toyed with that idea, right? I don't think it works. I think we have a better idea now. I also think it's very strange on philosophical grounds. Sort of a pre-Copernican idea to put one or another property relevant for life back on sort of a privileged footing. But the question is very relevant. Out of a random Big Bang doesn't come a universe full of life. So clearly something is missing from traditional Big Bang cosmology. And this, in fact, even the first traces of that problem are already evident in Lemaitre's writings in the 1930s.
Mm-hmm. I'll respond again with a few comments. You mentioned that the Lemaitre's primeval atom should evoke, or maybe he coined that term to evoke the importance of quantum theory at the beginning of time. And of course, that's so relevant to your and Stephen's collaboration and to his work that stemmed, at least in part, from Penrose's on black holes, because black holes sort of merge these incommensurable theories of the massive, so general relativity, and then the extremely small quantum theory. And we'll get to that. But first, I'd like to focus a bit more on the fine tuning. So the fine tuning, which you already said, is that our universe seems incredibly well orchestrated for life. I mean, if the mass of hydrogen or the strength of any of the four forces, there are so many different constants that if they were slightly different, life just couldn't evolve. And this raises this question of whether or not the universe is fine-tuned for life. Parenthetically, actually, I'll ask this, something that I found very interesting that I hadn't considered at all or heard at all until I read your book, is that one of these fine-tuning anomalies is that or apparent fine-tuning, let me put it that way, anomalies, is that our universe has three large spatial dimensions instead of, say, two. And this had never occurred to me. What would a two-dimensional universe look like? And if it, I mean, the pictures of the cats, and you can tell I like cats, so I like your. And actually, maybe you can't, since we've had to turn the video off. But I like cats a lot, and there are a lot of cute pictures of cats in your book. But why would a two-dimensional universe apparently be inhospitable for life? And I think that's a mini question. The second question that follows, though, is, well, I'll let you answer that first.
Oh, it's just you need a certain level of complexity, right? In order to have something, in order to have the possibility to reproduce. It's not, of course, excluded, but it seems, strangely enough, 3 seems to be the optimum number, because you could also ask, well, why not 4 or 5? But more spatial dimensions often also become problematic if only, you wouldn't even have stable solar systems in more spatial dimensions. So there seems to be something particularly habitable about 3. Enough to have complexity and not too much to have, perhaps in a way, too much randomness.
Okay, great. Well, so where I was going to go next, that second question that I alluded to, is one of the very important foils in the book to your collaboration with Stephen is Andre Linde and Leonard Susskind and some other string theorists' way of dealing with fine-tuning. And this theory is that of the multiverse, or the string theoretic multiverse. And maybe you could say briefly what this theory was, and then why Stephen found the anthropic reasoning in it so odious, and why he rejected it and ended up looking for other ways for accounting for the apparent fine-tuning that you two ended up developing with the top-down cosmology. But you don't have to worry about that yet.
Yeah, right. So the multiverse as an idea to, an explanation, so to speak, for the fine-tuning of our universe was in fact in full swing and very popular in the late 90s, early 2000s. I'd say it sort of started with Linde's work on inflation and eternal inflation. So Linde realized that, maybe inflation, the very early phase of expansion, of rapid expansion of the universe that produces the seeds of the galaxies, maybe inflation doesn't stop and produces not one universe, but many, or maybe even infinitely many. And then this sort of got combined with developments in string theory that showed that there seem to be so many different ways to compactify their 6 extra dimensions, producing so many different physical worlds of our experience with different particles, different forces, and so forth, that, perhaps combined with eternal inflation, all those worlds are out there. And somehow this appealed to scientists, cosmologists, I guess because it gave such a radically different angle to consider these fine tunings. Maybe they're just, maybe all those different universes are out there, and we're just lucky. Maybe most of them are lifeless. And once in a while you hit the jackpot or so. That said, the problem with the multiverse was there from the start as well. These theories of eternal inflation, which produced all these different universes, they did not say, nothing in those theories gave any indication in what sort of universe we should find ourselves. These were standard physical theories where there is no mention of any observer or any preferred observer. Hence, as you say, they go together with the Anthropic principle as an additional post-selection principle that is invoked to select this or that universe. The problem with that is that it becomes the universe you end up with depends on the kind of anthropic considerations you employ. You might have your view of what constitutes an anthropic principle. I might have a different view. Someone else might have yet another view, and there is no rational way for us to agree, because we can all have our own preferred anthropic property of the universe that we employ to select one of these. And so the theory of the multiverse, because of that problem, it's known as the measure problem in cosmology. We don't have a good measure to compare the relative weight, so to speak, the relative importance, the role of different universes in the multiverse. And that problem was there from the beginning. In the 90s, when I was a student of Stevens, it was already clear that there was a problem. It was not clear what we should do about it. I think the general expectation was that somehow the problem was going to go away. We were going to find some sort of resolution that we could all agree on. But then gradually it became clear that the problem was rather fundamental. The theory of the multiverse is just simply disconnected from, I would say, our position as observers within this universe. It doesn't take this into account. It's a theory that tries to describe the cosmos as a whole as if we're outside, as if we're looking down upon this huge ensemble of universes, and we use some sort of principle to select ours. It takes, in other words, a kind of godlike view on the cosmos. And of course this is wrong, but physics has proceeded that way for centuries, and so why not try? And so, that's roughly, I think, the situation in the late 90s, and I sense that Hawking was so worried about this measure problem that he thought there was something wrong with this entire multiverse idea. Of course, this didn't mean he had a solution, but he felt that the measure problem was in fact the cosmological analog of the famous information problem inside black holes, a profound paradox that arises from bringing together quantum theory and relativity not in the right way. So that's, I think, what the multiverse context of the late 90s, early 2000s, what that was about.
Great. And I'm really glad you mentioned two really important things for me. And one is that observership was one of the crucial problems for Stephen with the multiverse. And then, of course, it became integral to the top-down view of cosmology that you two would later take. And the second thing that's so important is black holes and holography and Hawking radiation. And we'll get to those aspects of black holes, I think, in a little bit. But I identify three sort of stages, and I'm sure it's much more granular if you look at the day-to-day work of Stephen over the past 50 or his last 50 or 60 years. But I identified sort of roughly three stages. There's, of course, the top-down cosmology. Then there's the no boundary theory that happened before that. But it all begins with Penrose's early work on the genesis of black holes, and then Stephen's subsequent work on a singularity at the beginning of the Big Bang. And so how did Penrose, or what was his conjecture about the genesis of black holes? And then how did that lead into Stephen's work on the Big Bang?
Okay. So you're right. Indeed, I think there are three stages. I think there are sort of three stages in Stephen's thinking about the Big Bang. The first stage in the 60s is directly inspired by Penrose's work on black holes. So black holes are, of course, another famous prediction of general relativity. It took years and years to understand that black holes are a physical prediction, not just some sort of mathematical curiosity of the theory, but that black holes really form in the universe when heavy stars run out of fuel and die and implode. And that's a famous prediction by Oppenheimer. But then Penrose came along and developed a whole list of new techniques in the 50s and the 60s, through which he could show purely on mathematical grounds that not just purely spherical stars, but any random star, any rotating star or a deformed star, that pretty much all sufficiently heavy stars at the end of their lives would collapse, and that there could be nothing to withstand that total collapse, so that you would eventually form a space-time singularity, where the curvature of space and time becomes infinite, where the theory of relativity breaks down, surrounded by a horizon, a surface beyond which nothing can escape. So it's Penrose's work in the 60s that showed that, based on the theory of relativity, we should expect the universe, we should expect black holes to be an integral part of the ecosystem of the universe. And of course, that's how it turned out to be. And years or decades later, Penrose got his Nobel Prize for that, right? What Stephen did was essentially turn Penrose's argument upside down, or turn black holes inside out, if you wish, and use the same mathematical techniques to show that an expanding universe must have a singularity in the past, So in a sense, the singularity inside black holes is the end of time, and the Big Bang in cosmology, in the universe, is the beginning of time. So it's a very interesting situation. The theory of general relativity predicts its own downfall inside black holes and at the Big Bang. And now you can say two things, right? So now what now? And of course, the general lore, the general interpretation of these singularities is not that they're really there, that nature is somehow singular. No, the general interpretation is that the classical theory of relativity is inadequate to describe those most extreme phenomena. And so that quantum gravitational physics becomes important in those two really extreme corners of the universe, inside black holes and at the Big Bang. So once, and that's essentially what Hawking and many others began to develop afterwards, right? His no boundary theory that you mentioned, which is a theory he developed with Jim Hartle in Santa Barbara. That's 1983, so that's 15 years later. And many would say, I believe, that this was the first genuine quantum model of the Big Bang. Clearly, that whole idea that is central to the no boundary proposal, namely that the time dimension, when we go back in time, Stephen and Jim essentially turned that dimension into a space dimension, claiming that a purely spatial geometry is how you capture quantum gravitational effects. So clearly, that's a very strongly quantum mechanical picture of those earliest phases of the universe. And it has the important implication that, whereas strictly speaking, a singularity, the Big Bang singularity in relativity, if you take it at face value, you'd be led to the conclusion, whoa, the actual Big Bang is not part of science. And in fact, that was one of the reasons that Einstein didn't like the Lemaitre's idea of a Big Bang. Einstein thought, this is a dangerous game. This is going to mean a genuine beginning means science itself is breaking down. Whereas Lemaitre thought, well, wait a minute. If we include quantum mechanics, I think he had the idea that if we include quantum mechanics, we could hope to get a grip on the beginning. So somehow that's a very interesting situation. There's a priest astronomer, Georges Lemaitre, who's trying to tell Einstein that God has nothing to do with the Big Bang, whereas Einstein believed that the Big Bang singularity was a genuine problem for science. And so in a sense, Hawking's no boundary proposal proved Lemaitre right. It's a model of the Big Bang, which is profoundly quantum mechanical. It involves 4 space dimensions and no time dimension. Time is an emergent property, which Hawking and Hartle interpreted as describing the quantum creation of the universe. So there we have a model, and this was the main selling point of A Brief History of Time, right? Which explicitly includes the beginning in our scientific description of the universe. Of course, the problem with the original no boundary hypothesis is that out of that no boundary beginning became a universe that is essentially empty. by far the most probable universe to emerge from their wave function is one which has hardly any galaxy. So that was a big headache, of course, for Stephen. It felt right, but it didn't work properly. Anyway, was that an answer to your question? I think it was, right?
Yeah, that was totally an answer. But I'm going to ask for some clarification just to make sure that I have pieced everything together. So I'm wondering if returning to this initial search for the beginning of time at a singularity with the Big Bang is one way of putting a finger on this issue, that it's really the same as what is commonly thought of as the major quote unquote crisis in physics, though whether it's a crisis in fact is contentious, namely that quantum theory and general relativity are incommensurable in their present very successful formulations, because and while general relativity retrodicts, to use that word again, and gets us all the way back to the singularity, if there were one, at the Big Bang, the microscopic is the domain of quantum theory, and they're incommensurable because space becomes indeterminate and jittery at these very small levels. So you can't really get, things don't really bottom out in the singularity. And then that's where this no boundary fuzziness theory emerges from Hawking and Hartle. And then the problem that stems from this, like you said, and this is where I think, if assuming I've gotten most of it right to this point, this is where I need some clarification. When you say the universe that comes out of this no boundary theory is empty and no or very few galaxies form, if you could explain what that means, or why this is what follows from that theory.
Yeah, good. Okay, so right. So a few points, perhaps. So you're absolutely right that the idea of Stephen's no boundary proposal was to replace the classical singularity of relativity with where the theory breaks down with a smooth, fine, sort of rounded off past, which is not something you can do in relativity, but you can, and that was sort of the crux of his theory. You can do that by considering these purely spatial geometries, which Stephen claimed capture profoundly quantum mechanical aspects of, as you say, fuzzy time, fuzzy space. But and so you remove the singularity by going from classical to quantum gravity. But this no boundary construction, you can't get just any universe out of it. That's the key point. If you take the vast majority of expanding universes that exist in relativity, you can't remove the singularity. You can't get them from a no boundary creation event. So that was also the beauty of the theory. The no boundary description made us zoom in on a very special subset of universes, namely those universes which involve an early phase of rapid expansion, which we know as inflation. The no boundary proposal of Hawking and Hartle is very much a completion, a quantum completion of inflation, of the origin of inflation. And that has a lot to do with the fact that inflation is a phase in which the universe is dominated by some sort of dark energy, by some sort of field that drives an accelerated phase of expansion. Well, it's that same kind of energy that you need for that no boundary construction to round off the past in that purely spatial manner. So somehow there's a marriage between inflation on the one hand and the no boundary idea of Hawking and Harter on the other hand. So far the good news. You get only very special universes out of this no boundary idea. Or put differently, if the universe is in the no boundary quantum state, it must have some sort of early phase of inflation in order to exist at all. Now the bad news. Any quantum theory, the quantum theory of a particle or any wave function, will assign probabilities to various scenarios. The wave function of a particle will assign probabilities for you to find it here or there. And so evidently, people looked at the probabilities for these different inflationary universes that the no boundary theory predicted, was providing. And then came the bad news. By far, the most probable universe was a universe which had just a little bit of inflation. Just enough to exist, frankly. And so just a whisk of inflation, which produced a universe which, maybe had a few galaxies, but nothing else. In order to get a universe with a lot of inflation that looks like ours, say, you had to go down far, far, far into the tail of the no boundary wave function and try to find it there. So that was a major issue with the early version of the no boundary theory.
Well, maybe I followed completely, but maybe this is a better way of, I think I followed completely. I should add that caveat, but maybe this is a way of better expressing my question and quite directly where I need clarification. So the creation of a black hole a la Penrose is sort of the inverse of the Big Bang singularity. That's what Stephen realized. And the creation of a black hole when a massive, incredibly hot star goes supernova is an incredibly violent event that involves an insane amount of energy. And then this, played in reverse, but on a cosmological scale, is the energy that provides for the expansion of the universe and the creation of all these galaxies. But the no boundary models without a singularity just don't have the energy necessary to produce the inflation that would require for the sort of universe we live in.
Oh, yeah, I see where you're going. I'm a little reluctant to draw that analogy between black holes and the Big Bang so strongly. They're both singularities in relativity. I see your point, but I think by the time that we understand those singularities, and so the no boundary proposal is concerned with the Big Bang singularity, they will look quite differently.
I see. Okay.
It seems to me that the singularity inside black holes, it's really a final state. It's a high entropy state. It's the result of an evolution, whereas the Big Bang singularity must be a low entropy state. So, but okay. This being said, another way of phrasing the problem with the no boundary proposal is that it doesn't get you a sufficiently low entropy state in the beginning. A universe with a lot of inflation is a universe that starts in an extremely low entropy state, and that's what gives it so much power, so to speak, to drive a clean arrow of time and an evolution towards more and more complexity for billions and billions of years. Whereas a universe with just a whisk of inflation that essentially ends up empty is in a way a universe that starts in too much of a high entropy state and does not have enough of an arrow of time. Having an arrow of time is in fact perhaps the most profound biophilic feature we're after here. So there is some connection. Yeah.
Okay. Yeah. That perfectly clarifies what I was asking. And now I think without any further ado, we're ready to get to top-down cosmology, because we've seen how, while these first two stages were, I hesitate to call them failures, because they led to very important insights that got the two of you to top-down cosmology. But this is also where the book culminates. And just to introduce this idea, how does the Everettian theory of quantum mechanics, where there's no wave function collapse, but a branching into many worlds with every active observation, relate to cosmology and retrodiction, and then get us sort of started talking about top-down cosmology? And you don't have to worry about being too in-depth about what many worlds or the Everettian theory is, because that's been covered a lot recently on the show.
Okay. But I think it seems to be there's some sort of consensus that we need something like the Everettian formulation of quantum mechanics to do cosmology, right? Clearly, the old Copenhagen collapse formulation would be completely inadequate to predict the past, and this was kind of the key idea, right? We talked earlier about the multiverse being some sort of theory of cosmology where we sort of view the universe as if we're outside. Whatever it does, and the many refinements of Everettian quantum mechanics do, they allow us of a more general formulation. They provide us with a more general formulation of quantum theory that permits you to put the observer inside the system. And that's, of course, totally necessary when we are going to develop a quantum picture of the cosmos. So, yes, Everettian quantum mechanics, the idea there are many possible histories, is, I would say, central to our work. Also, I mean, we were working with Jim Hartle, right, who developed Everettian quantum mechanics together with Gell-Mann into what he called decoherent histories quantum mechanics, which envisions, it's interesting, right, which envisions many possible histories of any system, be it the particle or the universe, and the kind of histories that rise to the forefront, the kind of histories that become important, depend on the questions that you're asking. Because it's the questions that you're asking that define the partition of histories that play out, that are relevant, that enter in your thinking. And so those are the kind of quantum ideas that were driving our work. Yeah.
And then more explicitly, how does this marriage of Everettian theory and cosmology result in your and Stephen's new theory? So what is top-down cosmology?
Top-down cosmology is recognizes, firstly, that we are within the universe. Secondly, that there could be a whole list of quantum accidents along the way, and therefore that we don't necessarily need to live in the most probable universe. So top-down cosmology works backwards. It starts from our observational situation, and it uses and it reconstructs out of all possible histories the subset of histories that lead to our observational situation. So it works sort of backwards, rather than trying to understand or trying to predict on a priori grounds how the universe should be. We take, if you wish, a more historical perspective and look at the relative weighting or the relative likelihood of different histories leading up to our observational situation. So we sort of claim that this is akin to a kind of, or that this amounts to some sort of Darwinian thinking in cosmology, where you recognize that along the way there could have been many accidents, that there was an interplay between quantum random jumps and interactions or selection effects, if you wish, leading up to our observational situation, rather than a purely deterministic way of thinking about cosmology that would lead you to try to predict that we should be living in the most probable universe. And so somehow top-down cosmology combines Stephen's old no-boundary idea with the refinements of average and quantum mechanics, and this observership and this observer's viewpoint from within the universe in a new framework, a framework which is in which I would say, the old idea of a multiverse, of a giant space filled with different kinds of universes, is replaced with a multiplicity of different possible past histories, each with their own probability. And so somehow the key point here is that this resolves the measured problem of the multiverse, because the histories in top-down cosmology are all contingent on our observational situation, whereas in the multiverse, as we discussed, you're kind of lost. So we also sometimes say that whereas the multiverse, it's some sort of, the top-down cosmology is some sort of inside-out view of cosmology for this reason.
I'm wondering if you could explicitly explain what you mean by observation and observers, because this is so crucial and leads to a lot of confusions, I think, about quantum mechanics. And for people who aren't familiar with the history of interpretations of quantum theory, it might lead people to assume, and maybe this is something that you intend, that you're saying consciousness or people or astronomers are very important to the history of the universe and the beginning of time, which seems very unintuitive.
Right. So your question is, how do we model this giant observational situation we have around us. One could say that the collection of all our data constitutes some sort of giant question we're asking from the wave function of the universe. And we are using those data to reconstruct possible past histories of the universe. But then exactly along the way, and all those data, of course, they continue to increase. The universe today is still making, quantum acts of observation happen all the time in the environment, right? So observership is so general that it's impossible. It could be, that it's impossible to give one single answer. It could be performed by a human, by an experimenter, by a particle, by a single photon, by anything. You might, so I'm not sure where you're heading with your question. You might be asking, well, maybe how does it enter in the early universe when there's clearly no consciousness, no humans, no life? What's observing there? But observership in quantum theory happens even just through interactions of particles. So even the early symmetry breaking phase transitions in the universe, in the primeval universe, even those are quantum acts of observation. They're random. Some of them are random. The universe could go this way or that way, but random accidents condense, crystallize, in a sense. That's already an act of observation. That's already a classicalization, if you mean, of a random quantum jump, which then further influences the subsequent evolution of the universe. So in these earliest phases, I would almost say that the universe was observing itself through the interactions of the various fields that were involved. So you have that observership at all different levels, going from basic fields of physics to, even to consciousness. What layer of observership is important, once again, depends on the question that you're asking of the wave function. Depends on the question that you're asking of depends on what level you're interested in. If you're interested in human history, you're going to ask very different questions from the wave function of the universe than if you're interested in the earliest phases in which the laws of physics may be still crystallizing.
So to summarize some of what you're saying, and again, to make sure that I'm on the same page as you, the work you and Stephen have done suggests that we must reject this idea that we can explain the origin of time from nowhere, so to speak, on a priori grounds, and that instead our understanding of the origin of time must necessarily come from the top with whatever data we have. And this can't lead us back to some determinate beginning of time for many reasons we've already discussed. And it's top down because from where we are as observers, and this is what connects us to Everettian theory, is that the data points to many possible histories.
Yes, and so and it's top down because it uses, if you wish, our observation situation, including the number of dimensions and particles and forces as input into the reconstruction of possible past histories. Just like Darwin never considered all possible trees of life. He looked around for fossils and tried to reconstruct a tree of life that produced those fossils. The reason is the role of accidents. If Darwin had tried, like multiverse folks had tried to look at all possible trees of lives and looked for the most probable tree of life containing whatever, some Homo sapiens branch, he would have failed on all fronts. The multiverse is similar in my view. So by putting ourselves inside, you're avoiding that trap. But, and this is what you briefly mentioned, I think, now you might wonder, okay, from a top-down perspective, you reconstruct these past histories, but eventually you come to the Big Bang and your time dimension, if no boundary idea is right, your time dimension will morph into a space dimension. But from that top-down perspective, it's really the ultimate sort of disappearance of the physical laws themselves. So, whereas Stephen in the 80s would have phrased his no-boundary theory as a kind of law that stands above and beyond the universe, a law that describes genuinely the creation of the universe, the later Hawking completely turned around on this point and said that this no-boundary idea should be looked at in a top-down way, going backwards in time, and should be thought of as a model that describes not just the origin of time, but the disappearance of the laws of physics. And this is, of course, very different, because then the laws of physics become part of the evolution, just like the higher level laws of biology that we already know. So it's fun. I think it's a fundamental point, which of course we have. It's a new hypothesis. It remains to be developed both theoretically and tested ultimately experimentally. I think the best way forward is to use these ideas of holography to have quantum theory and gravity work together. Holography seems to build in that idea that when we go back to the Big Bang, you essentially run out of bits and you run out of laws and the past doesn't extend any further. So there are many open questions that this raises, but it's kind of, so I view this hypothesis as a sort of beacon, if you wish, that can guide further development and further research.
Well, two things. First, I just want to clarify, because you said that in some sense the universe can be thought of as observing itself, that you're not suggesting that the universe is conscious as a whole, or that...
Oh, no, not at all. Sure.
Right. And you're not suggesting a panpsychist theory either. It's just that observership and observation is a term of art that means different things. And okay, in something different in physics than it might imply in our colloquial use. I understood that. I just wanted to clarify that for my listeners, because some people might misinterpret what you were saying because they're not familiar with the term. But then second, and you just indicated the future directions of work on top-down cosmology, but I'm curious about how the theory has been received by the cosmology community.
Well, the theory predicts, top-down cosmology predicts a big burst of inflation. And furthermore, it allows you to differentiate between different inflationary models. So in that sense, the theory resolves the old measure problem of inflation. And now, of course, the key point is inflation right or wrong? So we're gearing up for the next phase of CMB experiments that are aimed at finally detecting that remnant contribution of primordial gravitational waves to the microwave background fluctuations. That seems to me the key the key first test of this kind of hypothesis. Once you have that, you can begin to refine both theory and observations. I'm not sure there are. The whole debate about the whole I'm trying to think about alternatives to this theory that address the measure problem, but the whole field, the whole discussion seems to have died pretty much, because the paradoxes associated with the multiverse, of course, kept multiplying. So, once again, what would be the best way forward? There's a whole field now shaping up that has to do with applying holography to cosmology. I mentioned this just earlier. In my view, this is the best bet to put top-down cosmology on firm footing. In many ways, holographic physics, implements top-down almost automatically. You start from a boundary configuration and you work your way inwards. In cosmology, you start from a final configuration, a hologram, and you work your way backwards in time. So it almost seems to me that it's very well possible that if we manage to put holographic cosmology on firmer footing, the top-down viewpoint will become almost evident. And that is also important because it's only when it's really on firm footing that the predictions are going to be, that one can refine the predictions and that you can make progress, right? That you can test it in greater detail and all that. So, as I mentioned, I view it as a key hypothesis, almost as which has both scientific and philosophical implications, but which is, of course, like all work in science, a step along the road.
Well, Thomas, your book is
there you are.
Extremely rich. Yeah, there I am again. I figured I'd turn it on again so that I could say farewell. And your book is extremely, extremely rich, philosophically, historically. It covers a lot of material and a lot of theory. And of course, in our time, we couldn't cover all of that. So I encourage my readers to dig into everything, my listeners, to dig into everything that's going on there. But I just wanted to make sure that we covered, and I think we did, the main thrusts of your work with Stephen and the developments of his thinking. But cosmology certainly constitutes the most thrilling and biggest field of humanity's endeavor to understand what the universe is. So thank you so much for having this conversation with me and talking with me. I really enjoyed it.
Thank you. Pleasure. Thank you.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.